Okay, so good morning, everybody. Happy Father's Day. If you're fathers, if you Father's Day, we are going to be fathers again. Happy Father's Day. If you are very young, just call your father, say Happy Father's Day. This is the CVPR. I think every year we have this tutorial on Father's Day. So my two sons, they send me texts, so I'm happy. It was a great talk CJ gave. It's great to have students like him. So, we are very proud of him. Did great work at UCF. He's working in bike dance. And if you know anyone, student like him, please let me know. I'm recruiting lots of students. It's very hard to find good students. So I'm going to talk about this paper. We have this CVPR where, we say where we are and what we are looking at. So as you have heard so far today, that the geolocalization means that given an image, we want to find out the GPS location of that. Okay, and it has these two main techniques: retrieval-based method. That's what he talked about. Most of the methods are retrieval-based method, and the other one is the classification-based method. Okay, so the retrieval-based method, as you know, that we compute features of an image, and then we compute features of the reference image, and we save those features. Then we just given a query image and get your model, and we get query features, and we already have offline computed the features of the reference images. And once you have those, then we match it and we find the best match, and that's the traditional way to do the geolocalization. Okay, now classification-based method is a little different. So what we do, we take the whole Earth and project on a cube, and with each side of a cube become a class. Okay, so that's kind of more similar to the ImageNet classification kind of thing, because there's a lot of work on that. And we take that, divide in 4 smaller classes, and then we can have some threshold. If it's too large, we can divide further, and we remove the classes which are too small, and so on. We can keep going there. So it will look like this. These are little classes, these in the whole Earth, and we can split and move, and becomes like this. We can keep going that, and we can have very fine classification, fine small cells. So that's kind of classification approach. So now when we are given a query image, we predict the class it belongs to. So we just have like a classifier, take the image and classify which class it belongs to. That's the idea. Now, advantage of classification-based approach are this very immediate prediction. Just run one forward pass, it tells you which class it is. It can cover the whole Earth. Okay, and then we can introduce different hierarchies. Hierarchies can be like continent, country, state, and city, and county, and so on. So there's some work in this area. Most of is the retrieval-based approach. So there was I think one of the first paper ICCV 2017, which use this approach, and it divide the Earth in multiple partitions like this, and essentially it computes these features. They actually had these two classes. They were also doing the retrieval-based method and also this classification-based method like this is shown here. There was another interesting paper in 2018 by Muller, and they actually combined these probabilities from different classification level, hierarchical levels, and they found improvement. So the idea is that if you know the image in Europe, then probability that's in France increases. Then if it is France, the probability that it's Paris, you can utilize this facts in Paris and Eiffel Tower and so on. Okay. So they call this individual scene network. So in addition to the hierarchy, they introduced the 3 scenes, indoor, urban, or natural, and they train these model like that, and they have these different scene classifiers, and then we combine these output to actually do the classification. One more method, which is a very recent method last year from Ramachandran's group, and they call it translocator, and they essentially use the image and at the same time semantic segmentation of image, and they do this the attention between these two, and it seems to help, and they have pretty interesting results. So now, given this context, so our approach is that we want to use transformer, as I said earlier. I think transformer is the right way to do. And our approach is a decoder-based architecture. And we are introducing this new notion of geographical queries. So queries idea is very similar to data object detector, which was pretty interesting paper from my point of view. So we extract features for each hierarchy and each scene within a hierarchy and using that queries. So we have 7 hierarchies, and the 16 scenes. And so in addition to that, we introduce a new data set, which is fair and which covers the whole Earth. And also we have results which are state of art. Some cases we have 40% improvement. Okay, so now previous work only gets one set of features for each query image. Our approach accepts features for every geographical queries. So we have 7 hierarchies, and we did actually ablation on different hierarchies. We found 7 to be good, and these are the hierarchies. As you see, as we go down, then we have smaller and smaller cells, and then we have 16 scenes. And we did actually ablation on different number of scenes, and these scenes are, shown here. Sports field, transportation, cultural building, and workplace and hotel, homeland, home, and so on. So then model is simple. So it has the encoder, then we have these learnable queries, and then we have a 2 decoder. And then once we get these output queries, we select the maximum one that goes to the classifier. And we have these classifier for each of these. So let's go in detail. So our encoder is the SWIN encoder, transform encoder. It works pretty well. And that has, it's pre-trained ImageNet, and that output is 7 by 7 by 1024. And then these are the queries we have. So we randomly initialize, and we have these scenes, and each scene has these 7 queries. Okay, and each query is tasked to extract the specific features. So we have total 112 queries, and each is a 1024 dimension, and we randomly initialize. And then in that, the 0th channel is trained to be seen confidence when we get output queries. Okay, so then we have this hierarchy dependent decoder. So where we have the encoding of image comes in, and then we have queries, and we have these standard self-attention and layer normalization and all this thing. So they are basically extracting the features, relevant features from the encoded image, which are relevant to queries. Okay, and so this is a standard thing that we take the previous layer of the query, do the layer normalization, multi-head self-attention, skip connection, and then here we are doing a cross attention. So this encoding of an image, okay, which is coming from here, and then the feed-forward network, so standard transformer. So after that, then we have this hierarchical dependent encoder. So in the previous one, we were using all of these together, all the hierarchy, but here we're going to separate hierarchies, okay? And we found out, that to be helpful. So, so the idea is a self-attention and feed forwards specific to each hierarchy. And so only thing will be, we'll have this change here. Now we have H, we only use the queries for that particular hierarchy to get the self-attention and cross-attention. Otherwise, it's the same thing. Okay, so after that, then we get these output queries, and then we select the the queries which has the highest performance, highest value, and that goes classifier. And the way it's trained is the 0th channel is the actual scene label. So average of 0 channel for each scene and highest value selected scene. And the last part is a classification. So that, as I said, that we will use select queries to go to the particular specific classification layer. And this is the idea that we are using this different hierarchy. So given an image, particular hierarchy, what class it is, then, next hierarchy, what class it will be, multiply these probabilities and get the maximum one. So that's it. So that's your model. Okay. So now we train it using the 6-layer hierarchy independent decoder, 2 layers hierarchy dependent, and these are all the hyperparameters. I'm going to skip that. So now how do we train this on the this network? So training data sets typically use the MP16, the Media Ablation Places 2016. And it is about 4.7 million images with GPS from Yahoo and Flickr. And it's shown here, the different areas where these images come from. And it's a subset of YFC, say 100 million. And it's not really curated data set, but it's widely used. So these are examples of the typical images from this data set. Now, the testing data set is important that you train on one data set and test on other data set. That's the important point here. So there are several of these data set, image to GPS, which is one of the earlier one, only 300 images. Then image to GPS 3K, which has 3K images. And these are the kind of distribution of these. As you see, most of these is North America and Europe, and all the rest of the world is not really covered. Okay. So these are the images, and they're mostly landmarks and so on. So that's the problem. And then there's the other one, YFCC 4K. Again, it's a 4K images. Then we have YFCC 26K, 26K images. But as you see, it's only North America and Europe, and not other rest of the world is empty. Okay. So these are the typical images. So what we did, we wanted to address this problem with the existing data set, test data set, so that it's not just simply iconic places, but it is more general, and also this Flickr images are taken from random locations, and it's not really uniformly distributed. So that's a problem. So in order to fix this, we collected random images from Google Street View, and so we want to make sure that geolocalizable and it can distribute all over the earth. So this is the distribution of our data set. It's a small data set, because it takes a lot of effort to do that. Otherwise, they also charge money. Google is charging money, and actually they don't want us to release it. That's another problem. Even though we contacted them for research purpose, still. So, but the good thing is it covers the whole earth. So it's very nice. As you see, we cover everything. So the way we did it, we pick a country with probability based on the surface area, and then pick a town or city in that country, and then pick a random coordinate within 5 kilometers of the town, city. So these are the images. As you see, we have images from all over the world. We have Denmark and Iraq and China, Indonesia, Brazil, and Peru, and Myanmar, and Colombia, and Mongolia, and Sudan, and all those things. Okay, so one thing is, in order to have a fair data set, what we did, we sorted the city based on number of images. Okay, then we took the bottom 10% of cities and plotted a percent of total images on the y-axis. And that is Lorentz curve. So here is this 10% of the representation for certain data set and it's a percent of images. So ideally, to be fair, you want to be diagonal. And this is our data set, and these are the other data sets. So I think we are getting close to this. Still, we have a long way to go. So now let me show you the results. So results on the image to GPS. So now this is a whole, Earth. So we want to localize within street level, city level, region, country, and continent, and within this threshold. And we compare with other methods, and we get pretty good result. As you see here, we have a state of our results. This is on 3K. Again, we do better. In a couple of these places, we are tied. We are not as good, but it's still, we are getting good. This is YFCC 4K. Again, we beat the state of art. And this is 26K. We beat the state of art. And this is our data set. As you see, this is a very complex data set. It's a very, very small percentage, less than 1%. And so this is long way to go. And we'll provide the URLs of these images, and people can, take those images and, use those. So this is like a distribution of these. This is the original data set, and within 250 kilometers, we can localize these areas. And as you see, different levels, we can show that how well we can do. So then we also did, how many layers in the decoder we should use, and we found out 8 to be reasonable on these different data sets. We also did how many, whether scenes are helping, when no scenes, and scene prediction and hours, that helps in both data set. Also number of scenes, we did ablation on whether no scenes or 3 scenes or 16 scenes. 16 were helpful. And these other data set here, we also did the number of hierarchies on the different layers of this dependent decoder. And that this is on the ablation encoder type. So we did it with VIT, swing, and hours VIT and swing. The way we use, we do better with swing. It's more ablation here. And this is kind of thing, kind of qualitative results. It shows you that, this is the image and different hierarchy. What are these, different scenes being highlighted? I mean, these are nice pictures, and some of them are meaningful, but not all of them are there. But just wanted to show you a nice picture. I mean, this is a deep learning, right? So as far as works, that's good. So there are more of those. Okay. So and these are the images within 1 kilometer and 25 kilometer, 200 kilometer, 750 kilometer, and so on. So in summary, we presented this first transformer decoder based architecture, which is a very different way to solve this problem, because this idea of queries is that you randomly initialize, you ask what is the relevant information from an image, which is, very nice idea, actually came from the transformer data object detector and so on. So these queries extract the features for each hierarchy, and how many hierarchies you want to use and how many scenes and so on. And so we propose this new data set, which covers the whole Earth, and also we get pretty good results. So conclusion, we started with geographic queries, and we showed that it's actually doing the job, and it shows significant quantitative improvements, and our quality results show model works as intended, and our new data set solves the limitation of other test sets. So the future work will be that, you can try this on other data sets, like there's this BDD data set, which is more localized. There were, I think, 4 cities. And one can extend this idea to video, which would be interesting. I'm always interested in that. And one can combine the retrieval based method with classification based method that, you can have the cell, because these cells cover bigger areas, not a one GPS location. Then within that, you can do the retrieval, and that can improve maybe performance. And finally, as a joke, so how about ChatGPT? Maybe we can use that. So that's it. Thank you. Yeah.
On your data sets, you have to give the data set you created or any other data set you use. Did you have to give a training data for each scene, or did you automatically generate the scene classification for the training data? Like you had 16.
Yeah. So we of course during training we know the scenes, and because one of the laws is the scene label after we get the queries, and during the inference it's just queries. We don't have to know the scenes.
So when you were applying it to other data sets, not the one you did,
Yeah.
you had to go and manually add the scene to all of them?
No. It extracts that information. That's an interesting thing, right? So because we have trained these queries are, randomly initialized, that they are learned. So we just input an image, and these queries actually extract information.
So when you were training on a different data set?
No, we just train on one data set. We only train on MP16.
Okay.
And then we use it on all other data sets.
And for MP16, you had the scene data?
Yeah, it's available. People can use it. Yeah. Yes.
Nice.
Can you speak louder? I think it should work if all these things we are doing, right? That if these we have trained this on outdoors, right? MP16 outdoor. So if you have data set for indoor, you train it, then the scene levels is different there. So probably you have to have annotation of those that in principle it should work. But we haven't tried that. Your specific.
And so you train it to some data set with certain granularity. And what happens if the test set has a very different granularity? So is it transferable? And another question, can you use the features for retrieval? Can you go and take the features and like any image classification, you take the
Yes,
and use it as retrieval, then you are depend on the classification or granularity.
Sure, yeah, good question. So see, the one thing is, as I showed you, that the data set we train is this MP16, right? So this is a distribution of this data set, yes? And we test it on these data sets, so, and I showed you result, it works. It's pretty good. So that answered your first question.
But do you assume that there is the same number of hierarchies in the test set, or you just?
No, we don't. We're not assume anything. We don't assume. See, that's the thing, that we only want to know the hierarchies and all this thing for the test, training data set. Then once it's trained, we just give an image and give us these. Of course, hierarchies are fixed. We have 7 hierarchies as we have trained, and it will give you within those. Yeah.
So if it's trained on a city, can you test it on a I don't know, jungle or something like that? Or
yes.
Build it that doesn't have any buildings, just have an intuition.
Yeah, of course. I mean, there has to be, as he asked Christian, the indoor versus outdoors, right? So, if it is completely different domain, then they will have a problem. But otherwise it'll be fine. I think second question you had that if you can use these features for different, just, for retrieval basis, right? Retrieval method. So in a way, yes, because we have these classifiers, right? So these features are coming to the classifier. So you can use, if you want to, that one of those hierarchy. Yeah. Yes.
The training set, like MP16 is obviously biased towards famous locations,
Mhm.
while
Yeah.
GSV is more fair and
Yeah.
homogeneous.
Mm-hmm.
I wonder if, do you think that training on a subset of MP16, like a more homogeneous subset, without too many images from famous landmarks, would help to
Mhm.
improve the results on GSV?
Yeah, maybe that's a good point. Maybe, yeah, can be done. I think in general we need a much bigger data set and cleaner curated data set. But yeah, that one can do that because MP16 is not, a lot of errors in that.
Okay, so let's thank the speaker again.